Thank you very much indeed. Yes, I've been kind of around in AI, spent most of my career at Cancer Research UK running an AI group, particularly focused on oncology, obviously, but also with a much broader sort of range of interests. And spent a few years in Oxford and at the Royal Free Hospital, where we had a clinical team until 2 or 3 years ago. Deontics is a company, I'll declare an interest, I'm one of the founders, which was spun out from Oxford University and UCL. I'm going to very much focus, I think, on the clinical end, that sort of downstream end from the basic science. I spent enough time around CRUK labs to know sort of things that bioscientists are interested in, but I hope you'll find this talk both interesting as a route map for the future of how you will deliver the results of science to the point of care, and also how we can scale up this field to achieve something which is of clinical relevance. And I think we'll touch on a number of topics that people have mentioned this morning. Okay, so it's working for me. So very quickly, I'm going to talk a little bit about AI in clinical decision-making, tiny bit of history that most of you won't know. Why data science is a bit different from what I call knowledge engineering. Talk about open clinical, which is a way of crowdsourcing and distributing medical expertise. And then talk about something which I know there's at least one person in this audience is interested in, which is something called rapid learning systems in healthcare. And see if we can pick up the interests of a range of people here. Okay, now I have to mention this man. He's really the person, a man called Tim de Domble, who was a surgeon at St. James Infirmary, St. James Hospital in Leeds. Did you know him, Brendan? But he was the first man who tried to use Bayesian techniques to support clinical decision-making. And he did famous work in differential diagnosis of patients presenting with acute abdominal pain. He was somewhat unpopular among his colleagues at the time. This would be in the 70s. So the only picture I could find of him was on a Spanish website. That's interesting. Because at that time, the clinicians, I think, thought the very idea that computers could do what they do was absurd and somewhat irresponsible. Tim was actually enormously helpful to us. With a couple of my colleagues, one was a gastroenterologist and one a medical physicist, we kind of built a version drawing on some of his data for patients with upper GI pain and built this little system, which we put out into a local hospital in South Yorkshire, which would kind of give you a checklist of things to ask about for patients presenting with bellyache, as Tim would have called it. And give you a summary of what we currently knew, no medical records here, just a summary, and then give you a quick calculation using naive Bayesian probability to predict what this particular patient was most likely to be suffering from. This is a quick summary of the results of that system. This is an error matrix. So given the 5 diseases that the system had data for, where the diagonal is the correct diagnosis, Tim had a gold standard for that. And the other things are errors, which are probably intrinsic to the data. It's not clear whether you can eradicate those entirely. However, this was very simple. We took the database of 400 cases, used that to essentially create a conditional probability table, and as for a particular set of symptoms for a new patient, would calculate the posterior probability. Now, I did, foolish as I am, because I had an AI background, I was taking a different approach, what some people would call rules-based. The decision algorithm here was just to add up the frequencies of different patients with different symptoms. The learning algorithm in this case was me, and I went through about 50 cases, if I remember rightly, and kind of invented a set of rules which seemed sensible to me and my clinical collaborator thought was sensible, and came up with something which was very simple and did produce a very similar pattern of results. Now, the reason I mentioned this was not because this was a breakthrough in gastroenterology, far from it, though I think what Tim did, it could probably be called that. But what it was suggesting there are many different ways of approaching how you build a decision algorithm. And that's really what I want to talk to today. What I particularly want to introduce you to, if you're not familiar with it, is really what's been going on in knowledge engineering in medicine and medical informatics over the last kind of 30 years. in which lots and lots of different kinds of efforts have been made to develop different sorts of systems. We heard about alerts and reminders this morning, using kind of rule-based and other sort of systems, recommender systems, decision support systems, pathways and workflows. These are all words you've heard about already. And of course, at the top, we had the last period of AI enthusiasm, expert systems, and now the terminology is personal care agents that you have on your phone or on your smartwatch that's kind of monitoring you and keeping track of all sorts of things that may be of medical interest. At the bottom end is stuff which has been just dogged and continues to dog this whole field, and big data people must worry about it too, which is the problem of most of the data are pretty dirty, a lot of it's non-standard, it's not coded in straightforward ways. Nevertheless, there is, as we've heard in this meeting, there are ways of extracting useful information at this end of the ladder, looking for signals in population data. What I'd want to introduce you to is that there's a kind of more meaning level, kind of clinically intuitive level, which traditional symbolic AI was concerned with, or knowledge engineering, which how do we capture knowledge, how do we formalize knowledge in a way that machines can understand it as well as people. And what I'm going to talk to you is kind of illustrate a little bit of that, how knowledge engineering over 40 years or whatever it is, some of the things that it can let us do, and then talk about how do we bring that together with the machine learning revolution, if indeed that it is a revolution, and we don't know that yet, but to try to get the best of both approaches. Here's an example. This is a picture of the multidisciplinary team, the breast cancer team at the Royal Free Hospital, which, for those who don't know, is kind of up the hill in Hampstead, in London. Multidisciplinary meetings or tumour boards in the States are bring all the team come together, the surgeons, radiologists, oncologists, and so on a regular basis to discuss all the patients they're currently looking after. Before we kind of came, what they were doing were having these meetings. They had little paper notes summarising each patient. And they would discuss, and it's the standard of care now pretty much internationally, bring all the people together who have different expertise and have them discuss the case in order to get all the different perspectives involved. What we did, or I should say my colleagues, particularly Vivek Patkar, who's a breast surgeon and responsible for for being the clinical lead on this project, but we put up a system that allowed them to kind of view each patient and look at the decisions that were being taken, the data that we got, and it would potentially make recommendations on a wide variety of different topics. This, for example, is a view. This is actually a web version of the standalone version that we built at the Free, and that's something that is possible to demonstrate. What you see here is a summary. These are not real patients, but it's real data, but not real patients. We have a patient list. We have a first screen you would see for each patient is a summary. Under each heading, there's a, oh, sorry, I shouldn't have done that. Under these tab headings, there's a lot of different forms and data entry methods that capture data, and mostly in a structured way. Some of it's in a non-structured way. And then we can use the data at any time to make some recommendations based on a representation of best practice, in this case for breast cancer. So this is a short list, goes down to about here, a short list of things that the clinical team might be considering as appropriate based on UK and international clinical guidelines, whether this patient should be offered an axillary dissection or radiotherapy or whatever. And for each of those, we can also see the logical or the natural language rationale, the pros and cons, the arguments for and against that particular thing for this particular lady. In addition, we can drill down back into the original documentation. We make it very clear we haven't done any natural language processing here. We're not extracting knowledge from documentation of this kind. The tools we've developed allow you to mark those documents up and create manually the logic that's needed for this kind of method. But nevertheless, it gives you a deep knowledge. This word deep is being overused. A kind of deep insight into not just what is being suggested with the pros and cons, but but also the rationale. And we can potentially go into looking at data as well, incorporating statistical models. This is looking for this particular patient, what would be under different chemotherapy regimens, what would be the likely 10-year survival based on existing international survival data. And there's a variety of other things like alerts and reminders popping up and saying this patient is eligible for recruitment into a clinical trial, for example, or saying this hasn't been done, it's supposed to be done according to the standard of care. A whole variety of different services can be provided, for the MDT, for the multidisciplinary meeting to discuss. The decisions are taken by the team, of course, not by the machine. It's just providing the relevant information and data. This is another application that we developed with the American Association of Clinical Endocrinologists, who also write very high quality guidelines. The emphasis on this application was to model the workflow, model the clinical pathway. This particular patient who may have presented with thyroid nodules, for example, some information is recorded, some decisions are taken about whether to do a calcitonin or TSH test. Depending on the decisions that are taken, there are different pathways are followed adaptively, and we work our way through this. I won't explain the iconography, but it's a bit like a workflow diagram, which some of you will be familiar with, but it's much richer and captures the concepts of decisions and plans and actions and questions in a very direct sort of way that humans would find natural. So that's a couple of examples just from our work of how the kind of knowledge engineering approach can already deliver really quite versatile and capable applications. And certainly from our approach, we've published a dozen or so trials that all seem to indicate that we can improve decision quality, in some cases quite dramatically. Now I want to go on and talk about how do we hook this up to the kind of the world of data, the things most of these people in this room are probably more interested in. And this is what we call our life cycle. We start from some source of evidence-based medicine typically, or a standard of care. And what we're able to do is to capture a human who understands the subject matter expert can capture, using software, the formal version of the recommendations, the criteria, and so on, in order to create a version of that which is not human readable, but is machine executable. So a machine can follow that model and potentially give advice. What we're trying to do in the Open Clinical project is say we want to turn this into a publishing model. So everybody who has an interest in cardiology or whatever area, health and social care, in oncology, cardiology, any area of medicine, we don't believe that techies like us can write those pathways or build those applications. We want to give the tools away so that the clinicians in this room can say, I'm interested in IT, I want to create my own pathway on something I'm interested in, and then publish it on what's called the Open Clinical repository, where it becomes shareable. Some people then can download it. So maybe there's a cardiology team in Boston, in the States, who say, we've got a fantastic pathway for managing middle-aged overweight men with hypertension. We publish it, and then somebody in Bristol in the NHS says, we like the Boston pathway. We don't want to kind of do all that work all over again. We want to take it and adapt it for the NHS context. And we republish it, and somebody in Berlin or Botswana also has totally different context, and they want to kind of localize as well as give personalized information to the patient. Now, we can do all of that. The platform that Deontix and Open Clinical are working with supports all of that process. What we've never done, and which is really, I was certainly taken by surprise with the whole kind of learning phenomenon in AI, was say, how do we close that loop? How do we take data for every patient that goes through that pathway? How do we capture the data in a form that allows us to do the analytics and do some machine learning in order to feed into that process again and to maintain as new results, new trials, new data become available? We're learning. And this is a version of what Professor Brendan Delaney here is very interested in. He's the editor of a journal on this in this area of rapid learning systems in healthcare. This is what everybody wants really to be able. It's the kind of objective of so many people in trying to improve patient care. And essentially the proposition here is that there is a lot of existing AI that can deliver some of that. I'm not going to overstate my claim. So this is an example of a tool that we use to create pathways. This is one we give away. This is a commercial tool that's developed by Deontics. You can take the clinical guidelines and other sources, mark them up, create the machine executable version of that. There's no time for detail, but I'm happy to talk to people later who might like to know more. And then the publishing is, you can go onto openclinical.net, have a look at, we've got about 50 demonstration applications on there, a wide range of different medical areas. No machine learning at the moment, but applications built using the manual kind of knowledge engineering approach. And as I say, what we want to do is to kind of give those tools away to large numbers of capable people, interested and competent people who might want to share their own expertise and build those pathways and publish them. This is one example, actually not by a clinician, but one of my engineering students in Oxford in creating this as a page for one application for secondary prevention of repeat stroke. So the delivery, if we take that example, Anik Labadie created this application which provides support for a variety of different decisions. The patient's been admitted to the stroke unit, looking at lipid lowering, antithrombotics, anticoagulation. Maybe the clinician said, I just want a quick reminder of what I just need to know, what we do know about the patient. Just click on that. We get a form specific to this question, this clinical question of what was the best anticoagulant for this patient. And then you get a summary of the pros and cons for that individual. And that's all kind of out of the box. It kind of creates that interface. And the last stage, as I say, is the bit. Now, the rest of this talk is work in progress. We haven't done it, and I'm very interested to talk to people here who are interested in who have expertise that we don't have in the areas like machine learning, to say how can we kind of take advantage of what you know how to do and combine it with ours. And of course, if there are investors or sponsors in the audience who might like to support such work, we'd be very interested to have that conversation as well. What I'm going to do is what I call climbing the ladder. We can actually learn at lots and lots of different levels, and we've already heard a lot about looking for signals in vast amounts of population data. One of the things one also should remember, though, is that big data probably means bigger noise. That the bigger your database, the harder it is, not just to search the data, but the harder it is to find signals which are not spurious. So leaving that aside, statisticians and machine learning people understand that problem. There are techniques which allow us essentially to find interesting signals in data which maybe nobody quite knows what they mean or why they're there, but they've been opportunistically discovered in a complete set. So we can immediately learn that there are things that we need to understand. And climbing the ladder means climbing up each of those rungs, and the hypothesis is that we can apply different kinds of machine learning at different levels in order to give us increasingly meaningful, provide context for the data, to give it increasingly meaningful representation. So if we go, for those of you, I'm sure some of you worked with ontologies, things like Protégé from Stanford University, we might discover a signal. There happens to be some group of patients with A and B and C and D and not E. We don't know why that's significant, but it has some kind of clinical meaning. We want to kind of relate it to the body of medical ontology, medical knowledge, as clinicians understand it. The next level up, and there's a branch of knowledge engineering called description logics. We can use logic to describe many different kinds of things: situations, overweight middle-aged men with high blood pressure, events like cycle of chemotherapy, or white blood count recorded at end of cycle 4, or what have you, or pathways. Everything can be modeled in a formal, logical way. And given that representation, then we can learn rules, potentially learn rules and functions, some of which are traditional sort of big data statistical learning models, essentially learning classifiers of one kind or another for making predictions or selections of preferred treatments, examples we've heard about with sepsis and others, with alerts and reminders. But there's also a whole branch of machine learning that, for those of you not aware of it, should be. And that is symbolic learning, where you can learn from sets of data, collections of rules which are potentially intelligible to human beings, and more powerful methods which are being developed at really one of the major world centres at Imperial College in London. Steve Muggleton and Alessandra Russo have machine learning groups there. For those who are interested, I would certainly contact them. They don't work in healthcare primarily, but they are extremely able people in the symbolic machine learning area. The hypothesis is, and this is where it begins to get flaky at the moment, the hypothesis is we can not only learn learn rules, simply if then, but we can also begin to learn the intentionality behind particular decisions, what the options are when you need to apply particular rules. And the variety of different kinds of rules may have kind of rationale associated with them and evidence, which is grounded not only in the data, but grounded in the large knowledge base that clinicians carry around in their heads. And we aspire to be able to formalize and record on a computerized knowledge base. And lastly, and probably most flakily, we think it's possible to learn pathways, to learn process, not just dependencies and decision models and so on. So this is a hypothesis. I'm optimistic that this is a tractable scientific and technical challenge, and we're very keen to meet people who might see ways of using this kind of platform for their own purposes. So to put it all together, the starting point, I think we'll all agree, is there's vast amounts of data, oceans of data, that human beings can't cope with. What we need to do is to capture a lot of that data in a knowledge graph, which is a very formal graphical structure which can capture semantically rich representations of diseases, treatments, clinical pathways, and so on. And we can already do that to inform and support the clinicians or nursing team or even social care workers, we think, to help manage their work more effectively with less error, in a more timely way. What we've now, I think one would take advantage of is to learn from you, learn from people who understand the data science end, and say, how do we pull those two things together to get the intelligibility, the naturalness, the controllability of a traditional approach to AI and symbolic AI, with the power and the precision of numerical methods. So there's nothing. Just for those who are interested, anybody technical in the audience, the key thing about our approach is there's a language for modeling processes and tasks in medicine. And for anybody who's interested in the AI, there's also a paper in the Journal of Environmental Informatics that gives an overview of all of the cognitive science and the AI theory and foundations of that work. And I think my conclusions are, as a knowledge engineer, I claim that our practical skills are that we know how to formalize clinical practice in a rather rich and intuitive way. That knowledge representation is a key concept for the success of data science in medicine, because the meaning of data, and people have touched on this already today, is determined by the context, the medical domain and the clinical setting, and what's actually going on in the real world. All of that at the moment is and only some of that is computable, some of which has to remain with people who deliver the services. What the data science offers people like me is how to analyze data at scale, to find those signals, and to work with us in how to interpret them and perhaps learn from them, drawing on kind of analytics and machine learning, and then putting the two together. My prediction is that putting those two together will give us at least two benefits. The first is that, as I hope you cast your mind back to the breast cancer example, this is something that the clinicians actually like, this interface. It kind of talks medical language. It's not a bunch of numbers or whatever. Symbolic methods are superior are superior in their presentation, in the kind of potentially the communication between people and person and machine. But the statistical and numerical methods give us the precision and the robustness when you're dealing with highly variable populations. Thanks very much.
Thank you very much, John. That was really, really interesting, and it's so inspiring actually to see a marriage of those two different approaches.
I haven't done it yet.
Yeah, well, okay, maybe there's a question there. So, do we have any questions from the audience? There must be some. Over here.
Yeah.
Suchi.
That was a very interesting talk. Thank you. And I completely agree with you that I think in order to
Well, I was picking up on some of your points as well.
Yeah, I think in order to be able to communicate with clinicians and to build models that are safe and reliable, we will need to have some way of establishing common ground, and that often comes from, these quantities that we mutually understand, which is, these random variables like knowledge and semantics and rules, and these are really important. And even if they are stochastic systems, we need still a projection of them into something we believe the system is doing on the majority of cases as a quote rule. So so two questions. The first question is, have you, right now, are you getting people to create these pathways? There are a few different companies in the States that are implementing, going to hospitals, getting clinicians to implement pathways. And is that something that you found easy? People are they using the system? Do you have how many pathways do you have? Do you have any?
We've done a lot of it, but it's not easy. I'll just mention in passing, we did a project with University of Pittsburgh Medical Center, which is a 22 hospital group, and they were trying to say, how do we kind of do this kind of modeling ourselves? And I think the project was technically quite successful. We did some cardiology pathways with them. But the problem actually was completely business problem. That in the end, their own business model, in terms of how they might create a set of pathways, hospital, system-wide, which they then aspired to say, we can sell these pathways to other people. There was a whole set of issues surrounding actually doing that for real. There were kind of business obstacles. For us, I think, and the answer to your question is, if you look at the Open Clinical website, you'll find about 50 pathways of examples. But they've been developed by lots of people, half of whom were clinicians overall, not programmers, over a number of years. They're not medically credible anymore. They were kind of a snapshot over 5-10 years of work. But what we're now trying to do is to scale up and say we want to get to the point where we can really give all these tools away. And there's potentially 10,000, 100,000, healthcare professionals and scientifically trained professionals who could actively start creating pathways. These tools are very easy to use. But getting from where we are as a kind of post-university experimental project to the point where we've really got the resources to do that at scale is hard. Partly for business reasons, partly, but not for technical reasons. But I think, does that answer your question?
Yeah, I think in my experience, it's possible that I think it shouldn't be the case, but for some reason, it's possible.
I couldn't agree more. I couldn't agree more. You've just got to get there's what's that curve with the crossing the chasm. You've got to get to the mainstream. It's acceptance of an idea like this, that it's not crazy. It is tractable, and that just when you're at the beginning, it's a very slow process, chipping away and chipping away. So if there's a sponsor in the audience, please come and talk to me.
Any other questions? Here, thank you.
Brendan.
Thanks, John, for the double name drop for Imperial. Brendan Delaney from Imperial. I very much enjoyed your talk, and I think it was a very interesting counterpoint to some of the vision. I mean, it seems to me that we're moving from a point where people have applied very nice analytics to data that has been made at least somewhat tractable, and that moving that into the clinical domain, where it's enormously more complicated, is a real challenge. And I think one of the things that I think is critical is the number of different stakeholders around the room who simply don't speak the same language. And I wonder if you could comment on how we might try, as a community, to start to try and bring that more together.
Yeah, well, this talk is about, to some extent, trying to do that. It's trying to kind of reach out and to to engage with a lot of people with different backgrounds and different expectations. I mean, I've become aware, particularly over the last few years with this explosion of interest in AI, just how spending 20, 25 years or whatever it was working for Cancer Research UK, I'm not a clinician, but I kind of understood medicine is difficult and difficult in all sorts of ways. And when Watson, the IBM the marketing department got going and saying they were going to revolutionize cancer, well, I wrote a little blog that was gently critical of that, and it was called Clinical Judgment and Big Data, and the clinical judgment and clinical practice is absolutely not just classifiers, right? There's so many things to do. And I think now we're beginning to see lots and lots of people are aware that data by themselves are not going to deliver. Whoever made the I think you made the comment about data has a context. It has to have meaning. If the statisticians have to talk to the clinicians, to understand what an elevated PSA really means, then they probably won't get it, or they'll get a slightly impoverished version of it. And then, so what we're trying to do with Open Clinical is to empower the clinicians themselves, the professionals, to own this and not be totally dependent. They have to be partly dependent on technical people, engineers and software people and mathematicians, statisticians, but they have to own it and manage it and decide what it is that is tractable and useful, and not just leave it as a kind of technical program, which I believe will fail. And we can already see IBM's had its problems.